Hello, my name is Amber Patel.
And I'm Richard Van Natta. We will be presenting the Finsler-Hadwiger Theorem. Paul Finsler was a Swiss mathematician born in 1894. He received his PhD in 1919 from the University of Göttingen and was a professor at the University of Zurich. He also worked in astronomy and discovered Comet C. Hugo Hadwiger was also a Swiss mathematician born in 1908. He studied at the University of Bern and received his PhD in 1936, staying there as a professor until he retired. In World War II, Hugo Hadwiger helped design an encryption machine, NEMA, even better than the Enigma machine, with twice the number of rotors, making it exponentially more secure.
The Finsler-Hadwiger theorem was derived along with the Hadwiger-Finsler inequality, which provides a quick trigonometry-free upper bound estimate for the area of a triangle. It is a strict improvement over Weizenbach's inequality, which states that the sum of the squares of the three sides A, B, and C of a triangle is greater than or equal to 4 square root of 3's of its area denoted by K. The Hadwiger-Finsler inequality lowers this upper bound by the sum of the differences of the triangle sides a minus b, b minus c, and c minus a. These inequalities can be derived from Heron's formula for area, which states that area is the square root of the semiperimeter S times S minus A times S minus B times S minus C, where the semiperimeter is half the sum of the three sides of the triangle.
The Hadwiger-Finsler theorem can be used to solve the Boole's first problem, which is a square version of Napoleon's theorem on triangles. It states that if we draw squares from the four sides of a parallelogram, then the four centers of the four squares form a square. Napoleon's theorem has easy requirements and works with equilateral triangles drawn from the sides of any triangle, regardless of whether it's equilateral, isosceles, acute, or obtuse. So the Hadwiger-Finsler theorem has royal lineage back to the Emperor of France himself. After the video, we will challenge you to solve the Boole's first problem with it. Don't worry, it's a short proof. The Finsler-Hadwiger theorem states that for a square OACD and for a square OXYZ sharing point O, if we draw lines to the corresponding vertices from point O to point Y, from point D to point Z, from point C to point O, and from point A to point X, then the midpoints of these four lines, F, G, I, E, form a square. This theorem works for any two initial squares as long as they share a vertex, no matter the rotation. Let's take a look. This 1937 theorem is a specific case of the 1996 theorem of directly similar figures, which applies to all polygons. A figure is directly similar to another if you can rotate and scale the two figures so that they're the same. The other kind of similarity, inverse similarity, requires a mirror image operation. So your left hand is directly similar to another person's left hand, but your left hand is inversely similar to your right hand. However, your left hand looks like a right hand in a mirror. An interesting thing to think about is how there is no concept of inverse similarity for squares, hence why the Finsler-Hadwiger theorem doesn't mention them. What other sorts of figures don't have inverse similarity? Let's take a look at these clips to get a better idea of what direct and inverse similarity really are. So the theorem of directly similar figures states that if we have two directly similar figures, you can connect their corresponding vertices, take points dividing those lines in equal ratios, aka linearly interpolating the corresponding vertices equally, then the figure formed is directly similar to the first two. Proving the theorem of directly similar figures is tricky and requires quite the mathematical background in complex numbers and linear algebra, so leave it for now. Let's prove the Finsler-Hadwiger theorem.
First, notice that the midpoint of CO in the left dark red square is the center of the square, so it is also the midpoint of the glowing line AD. Likewise, the glowing line XZ is a midpoint of G in the right light red square. So now we have a quadrilateral DAXZ drawn in gray. We'll show why at the end of the video, but that inner quadrilateral that we want to show is a square. FGIE is formed from DAXZ's midpoints and is therefore at least a parallelogram. To show it is a square, we need to show that it has a 90-degree corner with equal sides. So notice that line OA is a 90-degree rotation of OD, since they are the sides of a corner of the dark red square. Likewise, in the light red square, OZ is a 90-degree rotation of OX. So we can draw two lines, AZ and DX, to get that triangle AOZ, which is a 90-degree rotation of triangle DOX. Since they are 90-degree rotations of each other, line AZ is perpendicular and equal to DX. Now look at the glowing triangle ADZ. Points E and I bisect sides AD and DZ, so line EI is parallel to and 1/2 of AZ, which is a fact we will prove as a theorem at the end of the video. Likewise, GI is parallel to and 1/2 of XD. Remember that AZ and DX are equal and perpendicular, so GI and EI are equal and perpendicular. We proved FGIE is a parallelogram, and now we know it has a 90-degree corner with equal sides, so it must be a square. Now let's talk about the theorems we mentioned but didn't show the proof of.
Earlier we claimed that if you have a triangle ABC and you connect the midpoint of line AB, point X, to the midpoint of line AC, point Y, then line XY is 1/2 the length of and parallel to line BC. Triangle AXY is similar to triangle ABC with ratio 1/2 by the SAS criterion. Since AX is 1/2 of AB, because X is a midpoint, angle A equals itself, and AY is 1/2 of AC since Y is also a midpoint. Already this shows that XY is 1/2 of BC. Because of their similarity, their corresponding angles are equal. So angle AXY is equal to angle ABC, and hence XY is parallel to BC.
Let W, X, Y, and Z be midpoints of the quadrilateral ABCD. We claimed earlier that WXYZ is a parallelogram. Consider triangle ABC, where W is the midpoint of AB and X is the midpoint of side BC, so WX is parallel to AC. Likewise, ZY is parallel to AC. Therefore, we can say that WX is parallel to ZY. We can use the same argument to show that WZ, BD, and XY are all parallel. Hence, WZ is parallel to XY, XW is parallel to YZ, which means that WXYZ is a parallelogram.
Now that you know the Finsler-Hadwiger Theorem, see if you can prove the Bose first problem. It states that if we have a quadrilateral and we use each side to draw a square, then if we draw a figure from each side of the square center, we get another square. Good luck.
We would like to show our gratitude to our professor, Dr. Muhammad Akbar at the University of Texas at Dallas, for giving us the opportunity to go beyond what is taught in the classroom to enhance our knowledge. We would also like to extend our deepest gratitude to our peers for their guidance and suggestions to improve our project.